Now it's time to discuss our solar system using what we have learned. In the previous videos we have discussed Newton's laws of motion, Newton's law of universal gravitation and Kepler's laws, and now we will put it all to use in the discussion of our solar system. Remember that physical laws should be general, so even though we're using our solar system as an example, the laws would also work for some other celestial system with a star and planets in another galaxy, as long as the system falls within the range of applicability of Newtonian mechanics. Before applying what we have learned, let's just go over the content of our solar system. The center of any solar system is a star or many stars, and in our case we have named our star as the Sun. Starting with the planets closest to the Sun, we have Mercury, which, as mentioned before, can't be fully described using Newtonian mechanics. Then we have Venus, and the third planet is Earth, where we live. Continuing outwards, we find Mars, and then Jupiter, which is the largest planet in our solar system, if you don't consider the rings of Saturn, which is the next planet. Finally, we have Uranus and Neptune, and depending on who you ask, we also have Pluto. In order to describe the orbits of these planets, we start with Newton's laws of motion and universal gravitation for an arbitrary planet with mass m planet and the Sun with mass m Sun. Now we can combine these laws to get an equation of motion for a planet orbiting the Sun. As always, g is the gravitational constant, a is the acceleration, and r is the radius between the Sun and the planet. To obtain our final result for our equation of motion, we note that the mass of the planet m planet is on both sides of the equal sign. So they cancel out, and thus we get the following equation of motion for our two-body system. A is equal to g m Sun over r squared. Now we have a general formula for our two-body system, and with this we can describe the motion of a planet orbiting the Sun. Notice that in this simple case the mass of the planet is irrelevant. Furthermore, we can also use this equation to describe how the Moon orbits the Earth. Before going further, it's important to understand what's going on with this simple example. Recall that Kepler learned that planets generally have elliptical orbits, thus r is not constant, but r is equal to p over 1 plus epsilon cosine theta. What's more, the acceleration a depends on the radius r as expressed in Kepler's second law. There is in principle nothing wrong with this equation we have derived, but to make it more clear that r is not constant and related to a, we need to rewrite it a bit. To express the acceleration in terms of r, we can use calculus, which was invented by Newton, and write it in terms of a derivative. Without going into too much detail, the acceleration of an orbiting object can be written using the derivative, which describes how the radius changes over time. If you want to know more about derivatives and calculus, let me know. Anyway, by writing the acceleration as a derivative, we now have what's called a differential equation. This is simply an equation you need to solve, and the solution describes the motion of a two-body system. As discussed earlier, our solar system has a lot of planets, and so far we've only been able to describe one planet orbiting the Sun. But actually we have done enough, since the planets in our solar system are more or less independent of each other. Thus you can just calculate the two-body problem with the Sun and each planet respectively, and this will give you a pretty good result. Thus we have just derived the physics to describe a simplified version of our solar system. But we can do better, since some planets also have one or more moons. So what we need to do is a bit more work. Using the same methods as before, we can write a set of three equations for a three-body system. Now this is a lot more advanced, but it is possible to solve these three equations and obtain a solution describing this three-body motion. And with that we can indeed include lunar orbits into our model of the solar system. If you would be crazy enough to consider four-body systems, you would not be able to solve it analytically, but you could get a good numerical approximation using a computer. If you have followed this series of videos, you should now have a good understanding of how you can make a model describing the solar system, just with the help of Newtonian mechanics. I think this is quite cool. Of course, if you wanted to solve this equation as we have discussed, it requires a bit more math, but the idea is relatively simple. I hope you found this series of videos interesting. If you did, please like and subscribe. Otherwise, stay tuned for more videos.